Okay, let's dive right into this. Welcome, focused learners, to today's explainer. Today, we're taking on a challenge that might sound just a little intimidating at first, but I promise you, it is going to be incredibly rewarding. We are going to completely break down the black box of deep learning. We're going to strip away the hype, the complex jargon, the massive data centers, and we're going to look right at the very heartbeat of artificial intelligence.
So, you might be wondering, what exactly goes on under the hood of a neural network? Honestly, it feels like a question that should require years of advanced mathematics to answer, right? But here's the secret. It really doesn't take a PhD to understand the core mechanics. It just takes a willingness to look closely at a few fundamental concepts. If you can add, multiply, and understand basic cause and effect, well, you have all the tools you need to understand how the most advanced AI systems in the world actually learn. And getting this, it means you'll never look at AI as just magic ever again. To prove just how accessible this really is, I want to start with a number. Just 150. It's a surprisingly tiny number, isn't it? But this little number represents a profound truth about massive, modern artificial intelligence.
That number, 150, is literally the total number of lines of simple Python code it takes to build a fully functional autograd engine. That's the mathematical brain that powers neural networks. This brilliant insight comes directly from Andrej Karpathy, a leading AI researcher who built a pedagogical library called Micrograd. He basically proved that the engine behind AI isn't magic, it is just simple math and incredibly concise code. Everything else, the massive tech companies, the supercomputers, that's all just about efficiency and scale. The absolute core logic is right there in those 150 lines.
Section 1. Unboxing Deep Neural Networks.
Let's see how this builds, because now we're going to unbox this system and look at its fundamental atoms. At the very center of Karpathy's Micrograd is something called an autograd engine. Now, autograd is just short for automatic gradient. Its entire job is to implement an algorithm called backpropagation. Hold on to that word, by the way, because it is the absolute star of the show. Backpropagation evaluates the gradient, and you can think of the gradient like a compass pointing toward errors relative to the network's weights. By doing this mathematically, it allows us to systematically tune the network, minimize its errors, and drastically improve its predictions.
Section 2. The math, derivatives, and slopes.
Now, to understand how that mathematical compass actually works, don't worry, we don't need massive algebraic equations. It's really just about derivatives and slopes. A derivative is simply a way of measuring how one single value responds to a tiny change in another value. So the crucial point is understanding exactly what a derivative is telling us. Imagine you start at a specific input value. Then you nudge that input slightly in a positive direction, by a microscopic amount we'll call h. Next, you just observe how the output function responds. Does the output go up? Does it go down? And by how much? Finally, you calculate that slope, the rise over the run. That slope right there is the derivative. It tells you the exact sensitivity of your output to a tiny tweak in your input.
I absolutely love how Karpathy frames this in his lecture. He asks, if you slightly bump up by a small number h, how does the function respond? What is the slope at that point? It's such a highly visual, almost physical way to think about math. You are literally just bumping a number and watching the ripple effect it has on the final outcome.
Section 3. The chain rule engine.
But okay, here's the challenge. A neural network is not just one simple function. It is a massive, sprawling mathematical expression with thousands or even billions of moving parts. To calculate the derivative of something that complex, we use the chain rule, which stitches all these tiny local slopes together. And this analogy brilliantly illustrates the concept. If a car travels twice as fast as a bicycle, and a bicycle is 4 times as fast as a walking man, well, the car travels 2 times 4 or 8 times as fast as the man. Boom. It is that simple. You just multiply the local rates of change together to find the global rate of change.
And that brings us to the real magic word, backpropagation. Backpropagation is, honestly, nothing more than the recursive application of this exact chain rule, flowing backwards through our computation graph. You start at the very end, the final output, and you flow the gradients backward. A simple addition operation, it just distributes the gradient equally. A multiplication operation swaps the inputs and multiplies the gradient. Step by step, the chain rule routes the gradient all the way back to the starting weights. Section 4. Building a brain cell.
So now that we have our mathematical engine that can evaluate derivatives, we can actually start building the neural network itself. Let's assemble a single mathematical brain cell, or a neuron. A mathematical neuron is a beautiful, simple model inspired by biology. Here's its anatomy.
First, you have the inputs. This is your incoming data. Then you have the weights, which act as the synaptic strengths. These interact by simply multiplying with the inputs. Then you add a bias, which you can kind of think of as the innate trigger happiness of the neuron, determining how easily it fires. Finally, all of that gets summed up and passed through an activation function. In micrograd, Karpathy uses a function called tan, which is really just a squashing function. It takes whatever raw number comes out and smoothly caps it between -1 and +1.
Section 5. Training with gradient descent.
All right, we've got our autograd engine and we've got our neurons. But how do we actually teach this network to be smart? Well, first, we define a loss function, which is a single number measuring how terribly our network is performing. If the loss is high, our predictions are way off. To minimize that loss down to 0, we run a continuous, repetitive recipe known as the gradient descent loop. Step 1, the forward pass. You feed your data through the network to calculate your predictions and see your total loss. Step 2, zero the gradients. You absolutely must reset all your mathematical compasses back to 0. Step 3, the backward pass. You run back propagation to calculate the precise gradients for all your weights. And step 4, update the weights. You take a tiny step, nudging your weights in the exact opposite direction of the gradient to make the loss go down. You just repeat this loop over and over, and the network miraculously learns.
Oh, actually, a really quick warning here. Remember step 2, zero the gradients? Literally, even Andrei Karpathy accidentally skipped this step during his demonstration. If you forget this, the new gradients from your current loop mathematically add on top of the old ones from the previous loop, accumulating endlessly. Your network learns absolutely nothing. It is a wildly common bug that has likely caused millions of dollars in wasted compute time and a lot of pulled hair for AI researchers, but it highlights exactly why understanding the mechanics of that 150-line engine is so mechanically vital.
Section 6. From micrograd to GPT.
Now, what's really interesting here is how we bridge the gap between this tiny pedagogical model we've just built and the state-of-the-art AI systems changing the world today. When you look at production AI frameworks like PyTorch compared to our pedagogical AI like micrograd, you see a massive difference in scale, sure, but not a difference in fundamental math. Micrograd is a scalar-valued engine. It processes individuals' single numbers one by one. It is built for pure clarity so humans can understand the chain rule. PyTorch, on the other hand, is a tensor-valued engine. It takes those exact same single scalars and packages them into massive n-dimensional arrays, or tensors. This is done entirely for extreme parallel computing. It allows supercomputers to process millions of these operations at the exact same time. But the underlying math, it is completely identical. So the magic of modern AI, it's really just the magic of scaling up. We can take Karpathy's tiny 41-parameter neural network and scale it all the way up to GPT models with hundreds of billions of parameters. Instead of training on 4 simple data points, they train on massive datasets scraped from across the entire internet. They might swap out a simple mean-squared error for a slightly more complex loss function like cross-entropy. But at the end of the day, they rely on the exact same principles: forward passes, back propagation, and weight updates using gradient descent. Why does this matter to you? Because it means the intimidating, seemingly magical AI you use every day is fundamentally just a scaled-up blob of the exact same simulated neural tissue we just explored.
Which leaves us with a truly fascinating fact to walk away with. We know the 150 lines of code that make it work, right? We know it's just the chain rule and simple derivatives. But if a multi-billion parameter model like GPT uses the exact same math as our simple 41-parameter net to suddenly learn how to write poetry or code, what incredible emergent properties are we going to see as we scale these identical mathematical principles even further? It's a wildly thrilling question. Thanks so much for joining me on this explainer, and keep learning.